measure cell potential of a cell. We've got a bit of theory on this first slide, and then we'll roll into the math equation on the next slide. So standard cells lead to measuring standard cell potential. So what's in a standard cell? I've been describing standard cells in most of our examples. It's when we have all the components of two half cells. Okay. So we saw examples where we had both copper and the copper 2+ ion in our original voltaic cell. That makes it standard. Okay. In our very first example, the OA was actually the copper 2+, but we need both for this definition. The other big part of standard cells is standard ambient temperature and conditions, 1 mole per liter, and this would be 25 degrees Celsius. When you're in a lab, it's often very close to 25. We can easily use 1 mole per liter concentrations, and we just have to make sure we put in all the chemicals on both sides, and we have these standard cells. Okay. The standard cell potential, you'd often think of that as voltage. The units are volts. Is the maximum electrical potential difference between the two cells. So there's a voltage difference. There's a pull from one side to the other side of those electrons. The greater one side wants to pull the electrons through the wire to the other, the greater the voltage. The analogy to gravity would be the greater the gravity, the greater the voltage. If gravity is higher, then an object is pulled more strongly to the center of that Earth or that planet. If voltage is higher, the electron transfers more energy as it goes from one side to the other. Low voltage, lower transfer of energy from anode to cathode. High voltage, a greater transfer of energy. Okay. We ultimately are going to be doing calculations and math, so we'll jump right into that. How do you calculate the E0 cell? This naught is just meaning standard conditions. Okay. So SATP, 25 degrees Celsius, 1 mole per liter, both sides. Okay. You're going to take the reduction potential of the chemical reacting at the cathode, and you're going to subtract away the reduction potential of the chemical reacting at the anode. Now the chemical reacting at the cathode is going to be our OA. So we're going to take the reduction potential of the oxidizing agent and subtract that from the reduction potential of the RA. Now through every one of my slides, I've always done the OA first and I've always done the RA second. Okay? If you wondered why did I always do the OA first, it's because I knew I was going to get to this slide. So if we keep writing OA first, RA second, we're just taking the top half reaction and subtracting the bottom one. Okay. So I'm going to jump into an example, determine the half reactions, and then go right into the standard cell potential given that cell notation. So a lot of solvent voltaic cells is done right with our table. So we're asked for the half reactions. I'm going to continue to do the OA on top, the RA on bottom, because the voltage is the OA voltage minus the RA voltage. So we're all set up to do that subtraction. The oxidizing agent is always going to come from the right-hand side. So you have to find that chromium 2,3 half reaction. Now it's quite low in your table, and it's negative 0.41 volts. So I'm going to grab that half reaction, chromium 3 plus aqueous plus an electron produces chromium 2 plus. I totally ignored that carbon because carbon is not in the table. It's an inert electrode. Then I jump to the beginning where our RA has to be reacting next to the metal anode, and that's actually the half reaction right below. Now that half reaction runs the other way. The elemental metal is the Ra. I'm flipping everything compared to our reduction table. So we've determined the half reactions. Now I'm going to grab the voltages that I haven't done before, and I'll keep my color coding. The blue OA minus 0.41 volts. The reduction potential for the RA is minus 0.45 volts. Notice I didn't flip the red voltage. Don't do anything to it. The equation says take the reduction potential of the OA and the reduction. Don't flip it to an oxidation. Okay? Really, the reduction gets flipped, but that's why we have the minus sign. The minus takes care of the flipping for us. So just take the numbers verbatim from the table. Okay? So we're all set to subtract those two. Okay? Do not multiply by anything. If you balance the equations, you'd multiply the half reactions by numbers. The voltages are just inherent to how much energy is transferred when an electron goes from one side to the other. It doesn't matter what stoichiometric coefficients you have. So from thermochem, you might be used to like doubling energies or enthalpies. Don't do that with voltages. So the E naught cell, the standard potential, so if we had 1 mole per liter of all our reactants, 25 degrees Celsius, we take the blue, we subtract the red, we've got minuses galore. When you do this properly in your calculator, you get a positive 0.04 volts. I'm going to put the positive in parenthesis. Voltaic cells should always be positive. If you get a negative number, you're either wrong or you flipped everything. You flipped your OA and your RA. Okay? Voltaic cells are always spontaneous. They're always positive cell potentials. If you're asked in a question, what is the cell potential, a lot of you will not write anything down. You'll find the two half reactions, the blue and the red in the table. You'll grab your calculator, you'll take the top, you'll minus the bottom, and you're done. You answer A, B, C, D in multiple choice, or you fill in the blank. One last thing to deal with. How on earth did we get these numbers? Like, where did they come from? When you measure voltages, you have to have a whole loop. You can't measure half a loop, okay, or half a cell. Yet we have all these voltages in our table for half a cell. Okay? Well, they're like our temperature Celsius reading. Celsius is relative to something, the melting point of water. In our redox table, everything is relative to hydrogen. That's been set at 0, the same way that Celsius is just set at 0. So the standard hydrogen, hydrogen ion to hydrogen gas at 1 mole per liter is our reference or our 0, and everything is measured relative to it. Every single value you see in the table was calculated by hooking it up to a hydrogen half cell, and whatever was measured on the voltmeter is the number that was put in your table. So if you make a standard cell with a standard hydrogen cell and a standard fluorine cell, and you hook up the voltmeter, 2.87 is what you'd get with that cell. And in future lessons, we'll learn about playing with this reference, and we'll dive a little deeper. But right now, we've got a 0. This wasn't measured at 0. It is our reference. Okay. Better OAs are above hydrogen plus, worse OAs are below it. Okay. The numbers are relative. Okay. So my nice summary of this unit, is laid out here. Okay, everything we've covered is nicely recapped